I'm an assistant professor at the mechanical engineering department. My name is Changhong Cao. I'm still building up my lab, but my lab is called Nanofactory. So basically the idea is to kind of streamline nanomaterial applications, synthesis and characterization. For example, we are working with the two-dimensional materials, like atomic thin materials. There will be a lot of applications there. The next generation CPU or GPU or memory devices, things like that. You know, the silicon-based technology basically reached their physical limitations, right? You heard of 7 nanometer, 2 nanometer, and things like that. So it's really hard to push the limit of silicon. So people are saying, can we find some alternative materials that are kind of not replacing silicon, maybe in combination with silicon or something, to create like a more powerful field effect transistor. Basically, the interface between the two materials can be subatomic level. If we can somehow leverage the two-dimensional material to make these transistors, the computing power of our GPU or CPU memory or things like that will be boosted quite a bit. You know, at the end of the day, you need to solve the manufacturing problem, right? And so the manufacturing problem of these kind of things, you know, mostly will be just assemble them together. And you know, one of the major goals of our study is basically trying to manipulate these two-dimensional materials, ultra-thin materials, like you're manipulating Lego blocks. What we want to do is pretty simple. Just pick 2D materials and drop them. You know, that's very simple. But you know, the 2D materials are very compliant. You know, wherever they stick to, they will just get stuck there. You know, it's very hard to peel them off and anything like that. So we want to do this like a tunable adhesion, basically. So in my lab, we have several different ideas. We're trying to use like ultrasound to shake these 2D materials off when you want it. And also we were trying to extend these controlling of these electrostatic force by controlling the voltage, external voltage, to do this like a controllable adhesion. And also another major areas we're focusing right now is basically we do multi-skill mechanical characterizations of thin films. So from atomic thin films like a graphene, right, to their interfaces, like the interfacial properties between 2D materials, as well as like thicker ones. Thicker ones, I mean a couple of nanometers. So we developed these kind of MEMS devices such that you can do tensile tests under scanning electron microscopy or transmission electron microscopy to probe their mechanical properties. And if you want to do, for example, thicker ones, graphene is like a 0.3 nanometer. For the van der Waals, it's like a couple nanometers. But if you want to do like, let's say 100 nanometers or above, and we have these kind of, we call it nano racks under AFM. So basically you can suspend these kind of structures either standalone or on a piece of a PDMS. And we can place that onto a miniaturized tensile stage. We can stretch them, and also we can bring in AFM cantilever to actually scan across the surface to see these kind of structures while you are doing the stretching. So you don't actually need to do that under SCM or TM, you can do that under AFM. So I can do a little bit of synthesis in my lab, but it's pretty limited. We can only do carbon-based material synthesis, but there are experts in the institute who can do, for example, boron nitride, MO2, and even some epitaxial growth kind of things. That's aspect number one. The other aspect is like, you know, we have a library of equipment that we can get access to, which is another huge benefit, because we're focusing more on the mechanical characterization, that side of things, but we're also sometimes interested in, for example, their chemical structures, as well as like, you know, electronic properties and all that. We have experts, we have the equipment available to us, which is excellent. At this stage, I would say, for advanced materials, if you can make it, I can find a way to break it.